Okay, so after we saw how we boot when we load the kernel as a boot sector, what we're going to see is what happens when we actually use a bootloader, okay? So we already saw some of the challenges, some of the annoying things like in GDB and QEMU, like with the breakpoint, like where GDB disassembles incorrectly. And now we're going to see some other things, okay? So this is an obj dump output of what we saw in the previous session, in the end of the previous session. And just pay attention that I give it like another architecture, okay, with x86, and then I see the exact same source code and everything looks great. Obj dump is usually less wrong than GDB, okay? And for those who say, hey, what about IDA and stuff like that? To be honest, like IDA does a very good job in these things, but IDA also have bugs sometimes, okay? Everything has bugs. That's life. And I'm going to probably repeat this mantra because you should never trust your disassemblers and your compilers, okay? So we already saw this part where we stopped at 7C14. Now let's use a bootloader. And when we use a bootloader, in QEMU, yes, we can use there any bootloader of our choice. We can have grub there, we can have uboot there, we can write our own bootloader over there. But when we provide a -kernel parameter, then essentially it's going to say, hey, I'm QEMU and I'm invoking my internal bootloader to load the Linux kernel image that you provide me. For this reason, I know that I need to jump to a very particular address that is 0x200 in a very particular segment that is 0x1000. And for this reason, what's going to happen is that our entry point is going to be 0x10200. Okay? Now, let's have a look how it looks like. Okay? This is the code, and this is the underscore start that we saw in the linker script prior to that. So what we're going to do now is this. We'll first show that the addresses that we saw prior to that, that is in boot sect, don't happen. Now, let's do this, okay? So if I now go, and if I run without a debugger, let's say, let's have a look at debug bootloader. This is going to be my line, and I'm just going to get rid of the debugger here, okay? So if I do this, I will see the following messages, and here I will see like my terminal, okay? Fair enough? Booting from ROM is from QEMU, and look what I have here. This welcome to ROM's demonstration is what I added in the beginning so that you have something that stands out. Input data and input len and netted size and so on are prints that are coming because I enabled a particular configuration. And in ARM, you would actually need in the source code itself to enable debug. But we'll get to it when I talk about ARM, okay? But these are prints, very early prints that use the BIOS routines to print to the screen. This is why I see it here. And I will not see them in the serial. In the serial, I'll start seeing with the Linux banner, okay? Fair enough? Good. Now, let's first prove that we don't even get there, okay? So I will use GDB. Now I will run this debug bootloader sh. And as the first port, I will use these addresses to just put breakpoints on them. Sounds fair? I'm going to do GDB, and I'm going to break hardware breakpoint. Okay, I'm going to connect first to the target, remote 1234. Then I'm going to break in this fellow, which I expect to not see, and then I'm going to break in this fellow. Okay. Now, let's also see. I know it's boot S, but never mind that I know that. And look at this. This is like something that actually is aware of some symbols, which is nice. But right now I'm not, because I didn't provide GDB with any symbol file, just connected to it. So I'm going to also break in put s because I know it. Okay. Maybe it's called and maybe not. So what I want to see now is what's happening on the screen, if something happens on the screen. So when I first stop, then it's going to be the QEMU BIOS. So I will continue to at least step over that. And look what's happening. Do you see this? See BIOS IPXE booting from ROM. This looks promising. This looks great. But what do I have in my commands? And we already know that we need to use disassembly of not only the program counter, but also of the code segment. So look what we have here. CS is 1020 and PC is this. So the address is exactly where I broke, right? So now I'm going to do display slash, let's do 20i, $PC plus 16 times $CS. And this is what I see, that the first instruction is jump to 1020C, 1026C, okay? I'm going to do that. And let's also add a display to see the code segment, all right? And let's also see the data segment. I need to give it like this. And I need to have it separately. So code segment and data segment. Look what we have here. Different values. Never mind the reason for that. But the values are different. And later, if you look like at the assembly file, you will see that there is a deliberate adjustment. Okay? But forget about it now because we want to keep it shorter. So I'm going to now step instruction, and I'm expecting to have a jump. Okay? So let's see what's happening. Nothing happens. Why? Because GDB has this problem with the breakpoints. So it's really, really, really annoying. I'm going to delete them. And now that I do the jump, here I see it. Okay? So that's where I am. So you see what's going on? So we have this. And I did the jump properly. And I'm in the instruction move DS to EAX. Now, in order to, we can of course step instructions and see and jump, and I'm doing the things like the address will go on, and then there might be jumps or call that will leave us to all kind of things. But I'm just doing step instruction, and here look what I have. I have the following thing: rep stos. This means store something at a particular way, at a particular place. Now, the particular place is going to be under ES and EDI, and it doesn't really matter what we do right now. But the important thing is that the moment we have rep, it means that we might be stuck here like forever almost, unless we know how many iterations of it to wait. And this iteration, this is like a loop. x86 have a complex instruction set, and it allows me to do a lot of things in one loop. So if I want to go past this, if I go a step instruction, every time I have this, then it will decrease by 1, right? So I can say, okay, I'm lazy. I will skip this 226 times, and then I will be in the next point, okay? That's what will happen. Now, I'm not even sure if what I have here is true, wrong, not sure what's going on. I will now move some value to EAX. Let's see what is the value of EAX before. And let's see what is the value of EAX after. Again, this is wrong. Like, what is going on here? Why do I see E866041D and the value here is really 41D? So, I mean, it's not completely wrong, but it's wrong enough. It's because GDB doesn't handle real mode so well, okay? I mean, you should care about the upper part. It's 16-bit, it's not 32-bit, okay? And it's AX, it's not EAX. So there are all kind of these things that you can know better if you disassemble, for example, externally, okay? Or sometimes if you have like a debugging information, like in the object file. So after this, we have call. And call goes to 3D0. Now, look, I have no debugging information. I have no idea what's going on. Yes, I can go and disassemble if I want 3D0. And at this point, I need to add also 16 times the code segment. So it does all kind of things. Like here, it looks like it returns immediately. Okay, what is the objective of this return immediately? And then it pushes and things like that. Now, where is 3D0? If I disassemble from the program counter, let's say I wanted to see x/50 I of the current program counter plus 16 times $CS, then this is the program counter, 3D0, and I see all kind of things, and D will probably be like down here, so I can look at some more. So I can start looking at the source code and see what is going on if I have the source code. And it's not a bad idea, okay? I can do that. But I want to tell you something else, what's happening here. So back to our current instruction, before the first jump that we have. So we have a call to something. And let's see what's happening here. Now, this is our header file, okay? This is the exact same file that contains the code that we used in the boot sector. This is the section bs text and bootseq start. And we jump on whatever the result of this guy is to 200, that as we saw in the linker script, I'm not showing again, is the address of start, okay? Prior to start, we have all kind of things, all kind of data words. Some things will be stored by the linkers. Some things will be actually stored when running, okay? When the kernel runs, it will store some things here. And some things will be, for example, section header. We'll have this global header that we looked at. So remember that was assert in the linker that says, hey, check if header is on 497 and section header started on 495. So this is why it is. This is byte 495 and this is byte 497. Everything makes sense, okay? So we have these ones. So if this is 497, okay? Then this is 498 because it's a byte, okay? And this is 499 and 49A. And here we have 4 more bytes. And here we have 2 more bytes. And this fellow, this first byte is on entry 512, okay? This on a 0x200. Before I messed up deck and X. So it's not 49A. It's going to be for 500. It's going to be, okay? And then we're going to calculate. So these are going to be 12 bytes. So look what we have at offset 512 here. We have this byte. This is jump, okay? And start of setup. So what is start of setup? It's the first jump that we had. It's this guy. What happens before? All kind of words that we skip and comments. So you see, the comments tell a little bit about like the boot protocol, what we expect to have here, okay? But we skip all of this. You see how many we have here? All of them are in what is called the header, okay? So it's a little bit hard to understand what's going on maybe because, okay, this is the address of start. Great. And back to whatever we debugged. Somewhere there was a call. Maybe it's called W, maybe it's called L, maybe it's who knows what. And there is all kind of things. How do I match these addresses here to the instructions here? So the idea is to either understand the code, which is a very good like a thing. And we already know that there was a jump to this label, to the start of setup. And we can see where is like the first call that we have here. There was all these moves, and there is like a jump, and jump to label 2F here, okay? And label 2F will fall through to 3. And here we have push W, ret W, after which we have CMP, that is compare, and a jump to set a bed. That's probably not it. We have all kinds of things, and then we have a call to put S. Now, getting back to context, I know it's hard to follow, but that's life. What I claim is that this one may be put S, but how would I know it without knowing the code? So the answer for that is like this. We're going to go to the object file that is supposed to represent it, okay? And we're going to go to boot, and we know that we're running setup.bin, so the corresponding one is setup.elf. And we know that we're having header.o, so we can just look at header.o if we want to, okay? And what we can do is several things. We can even use like nm and see what is like the symbol addresses. So I can go and do nm on header.o and see what are these things here. Maybe I will find something promising. But I see that u is undefined, and I see that main is undefined. That means that they do not come from this, okay? And I see these addresses that are not necessarily what I'm looking for. Setup bed is 62, okay. But maybe it is this, maybe it's not. So too many things are missing. I see underscore start, and it points to 11. Why does it point to 11? So what we saw in the linker script, back, I show you, is this was in the input directory, right? And so it's going to be under Linux Arc x86 boot setup LD. What we saw in the linker script is that we have this entry here start, okay? And we can see that if it is in a particular section, for example, in the section that is after this guy, then the address will be relocated, okay? So if header starts at a particular address and start has the offset, then I will add the offset at the final place, okay? So if I disassemble now, if I look at with the nm, for example, I'm not even disassembling, setup.elf, that is the linked file, then I will see other addresses, okay? So if I look, this is A20, they're not sorted, of course, okay? It's wherever like symbols are defined. But I can go ahead and look like for if I see underscore start, and I see that it is 0x200. So this is exactly where I put the breakpoint and where I jump. And the offset from this in the memory is 10,000 because this is where I'm loaded. Great. So I can tell you from experience that everything here until one phase, you add 10,000 and you're done. Okay? So if we add the address of 3D, and I want to prove that it is put S, I can see this. So we have 3D2 in my static file. Here I have call W to 3D0, and sometimes the call will not look exactly as they are, okay? Then if I single step here, I will see that I'm indeed in 3D2. And if I look at the implementation of puttest, I will see that this is how it is. And I will see that it calls 346. Now let's prove it, and now I'm going faster. I'm going to do something else. I'm going to do obj dump. I will disassemble it, okay? -D to this guy. I will do less, and I will jump here to puttest. And I will see that this is what puttest does. It has this guy, and then it calls int call. What is int call? Let's go to int call. Is it here? Many people call int call, okay? Here is int call, it's 2e9. Oops. I went lost. Int call. Let's look at int call. Int call does some trickery. It doesn't matter what it is, okay? And then it calls int, okay? Now the trickery, in long story short, is to get like the number of interrupt, like 0x10, 0x16, and so on. So this put s calls int call, and I'm telling you it is using int 10, and I could prove it to you, okay? But I'm not going to do it because this is not the important thing. What is important is that we saw now how to match some of the things in the code, okay? So now let's prove it again with the debugger. So we were somewhere in 3D2, okay? And I will want to get out of here either by escaping, either by a, I cannot do finish and get back. I don't have like the frame context that I would expect in a well set up kernel or like in user space. I do not have this. What I can do is disassemble and see what putTest does, and hopefully the bad things are not so bad, or hopefully I can get back, and hopefully I can do like the jump, or hopefully I will get to the red point. So let's try and see if I can get to the red point, okay? So I'm going to go here, and in this particular case, I am going to put the breakpoint at the red point, hoping it is the same address. And I will try to see what's happening here. So I'm doing now cont, and you see what happened? Welcome to Ron's demonstration. Bootheader says hi. So I could actually go and look before that, break before that, and see that I am the one who calls it, see the value in the register, and see that actually the address of like this header is what I was interested in, and so on, okay? I can disassemble to the lines that are before. I can do all these kind of things. So this was this putS, which is great. Okay, so now we'll do return. And I'm stuck because of the breakpoint things. Yes. And when I have this return, look what's happening. We have call W and to main. This looks promising. This looks nice. Now what is main? And what do we have here? And how could I like add debugging symbol to this guy? So in order to see where I want to add my debugging symbols, I need to understand the else structure. Okay, I'm putting it again bigger. If I go ahead and do, for example, objdump-h, or I can do readelf, or I can do all kind of other tools. To set up .elf, I'll do it with hw, so to be white. I see that there are the following sections. Now, when I add a symbol, and it is a very, very, very important observation, what's happening if I just do like file in GDB or do GDB blah blah, then what's happening is that it's going to take the load address of the starting command in this case, and if add it to whatever is like currently like the memory base, and if I don't give it any parameter, it will just say, okay, the text begins there. It will match whatever is like in the text and do the adjustment of like wherever it is the VMA on like the file itself, okay? What is the offset on the file story and what is the VMA instruction? It will add the required relocation. The problem, and for those of you who are seasoned developers and break their head how to develop kernel modules, for example, the problem is that there are a lot of sections that are not text. So you need to know addresses. So what you need to do, the math is something like this. You are going to add a symbol file you give it the address of text, okay? The address of text on your symbol file. You have to. This is what it is. And for every section, you're going to do this: sec name and address in memory. Super important, okay? So if I want to see, for example, what is start and where it is, I'm going to do, for example, opt jump on one of them, okay? Let's say on VM. Oh, sorry. Let's say on this setup.elf. And I can disassemble everything. If I also disassemble the data, you see these guys? I see boot sector, I see start 2, I see message loop. I see things that would not be available for me because it's not the code, okay? I see the header that when you xdump, you will see what it is. And I see that underscore start is at section dot header, all right? So I have different sections. Here I have entry text that has start of setup. And here I have init text that shows me int call. And here I have put char and so on. Where is text? Text starts with empty 8042 at 45D. And I also need to tell it what is the load address, like on the target itself. And so I'll need at this phase, because later this will change, to add 10,000 to it. Okay? So what I'm going to do is add these sections. Now, I wrote it from before, so I'm going to just see what they are. Okay? So let's see. x86 from bootloader. And what I'm going to do, I did several steps just to show several concepts. So I'm not 100% sure that in some places I like deleted things deliberately, okay? But these are the different sections in the file. So BS text start is 7C00 in memory, as you know. 045D is the start of text. So this is what I give it as the parameter, okay? And for example, header starts at 1EF. We saw it also like in the linker script, okay? So let's see what's happening when I add the symbol file. It asks me if I want to. I say yes. Okay. Give you a second to see what I'm doing here, that I'm not bluffing. And now we'll try to disassemble again, and look what I see. I see data. Okay. So I see that I'm now in infinite loop plus 9. This is infinite loop. Okay. I'm after the call to put test. This is plus 9. Okay. And I have a call here. So there are some trickeries, okay? Like sometimes, first of all, now I don't know where main is. So let's see where this main is. You didn't even know there was main, right? Because I didn't jump to it yet. But we will look at main, which is like a C code. And sometimes I cannot both see the addresses I jump to and the labels themselves in the right way. And if I give the wrong offsets, I will definitely see things in the wrong way, okay? So let's have a look at which section main is. And I know it comes from the object file main.o. I'm just going to do objdump-d on main.o. Should have did -h, but never mind. Main comes from .text.startup, okay? So if I look here, I redirected .text.startup to 0x12ec6. And if I'm lucky enough, then it doesn't overlap with something else. Let's see, what are the section here? I'll do objdump -h w to set up elf. And text startup is supposed to start at 2ec6. Okay? So this is 2e6. it didn't catch now. But let's see what is this address. So first of all, maybe it did catch because look at this. 2EC4. Why? Because this is what GDB decided. If I do SI, boom, I'm in main. All right. Too bad you don't have a video of me. I like to be dramatic when I see this. So now I have something with debugging information, and life is good. And now let me just tell you, and I'll make like a story a little bit shorter, what main is. So-called what we did is we jumped over all kind of things that I'd be happy to explain another time. We saw this in the linker script. We saw that GDB misinterprets it. Or maybe we didn't see, but it misinterprets it. Like some of the things that like it does wrong, terribly wrong, is like this is like main, what we saw now, that it looks like at the wrong things, okay? And it doesn't understand like what is going on with this EAX, all right? This is like what we have like with, this is with debugged symbol already, like this has like that it pushes and does this where actually we have CMP, okay? So on the left-hand side, we have a GDB, and here we have like object. So there are all the kind of things that we need to take care of. It's very, very, very important, okay? So far we proved that we skipped this 200. We did all kind of things. We saw how to disassemble object dump. We saw now that GDB sometimes is wrong, but I did not talk about exactly what has been doing here. There's like a fix up that makes the code address equals the DS. And if we want to see what's happening, and this I skip now, you can see also that we're like when we return from a function, what do we return to? We return to whatever is on the stack. So as I said before, you need to be very, very, very careful to not, when you inspect something, to also multiply it with the relevant segment, okay? Now, other things that can be if I put like the instruction in the wrong way, like this is not necessarily get a char timeout, okay? This could be something else. This could be main. This could be push. This could be like disassemble. This depends on like what you look. I don't even remember like what I ever. I think this is main. What I see here, and I'm sure I know this is main. Let's see it. This is somewhere over main, okay? Like where we have pushes. So actually, I don't remember exactly what it is that I took here. If I look, what is 12EDA? Let's see. Yeah, I was right. 12ED. So here we have another problem, like it disassembles like the wrong things even. Okay. So there are all kind of things that like you need to be aware of. Otherwise, they're like, huh, what's going on? So I'm not going to go over that. I will tell you that what I said like before, there are sometimes bugs like when we try to call to main, as we saw that was like 2 bytes before, or when you try to call put s here, that it will not show you the symbols. But if you're careful and adjust the addresses properly and so on, then everything goes well. I took it from one exercise that I had, okay? So what is the next phase? The next phase is this. We understand that we call main. Now, let me show you what main does, okay? Main is actually a C file that does this, put s run 0 because I put it there, and then a printf with an address because I put it here. This will be the address of main. So we'll see what main thinks its address here, okay? And it will not be what the address is in memory. Very important to know. The way like to debug, if you print all kind of memories, you will not necessarily see it. And then it initializes console, search for the debug option. And this is about like debugging and figure out things. So I'm not going to go over the processes because it will take time. But the important things here is that like we set the video mode, and here you can see later how the VGA like prompt select like mode, if you have VGA ask like how it's being done. And the critical thing here is that we go to protected mode, okay? So let's first see that I'm not bluffing you. I will go over some of the points here, not over everything, okay? And let's see. So right now, I'm going to get rid of the breakpoints, okay? Just in case. I'm going to see. This I didn't want. This I also didn't want. This I did want. So I have the symbol files. We've gone through that. And what I'm going to do, this is already past it. I'm going to do a hard breakpoint on when we go. We are right now here, okay, in 286. We're going to do a hard breakpoint on this address. Okay. So this H break on this. And it even tells me that the file is bootpm.c, which is interesting. Like it even has a file information. Why? Because this is how this particular file was compiled. And I loaded it, like the object file for that, it was linked with it. When we later strip it, it will not be available. So not all files are compiled with like debugging information, debugging symbols. Sometimes you need to have config debug info enabled for it, okay? So I'm going to now do some steps. And remember this call to 3D2 that we're supposed to have? Now we have bad. It's not. It just got the wrong mnemonics. So I did NI, and if GDB understood well what's happening, then it would actually skip this call. But it doesn't, okay? So here we are input S. I can go ahead and single step it. I will not do it, okay? You already know from my example what the result is supposed to be, right? So let's just prove it. And when I do cont, I go like into the next breakpoint, which is at the end of the file. So I already print these guys, okay? Now I jump to go to protected mode. I hope that it is like workable because, you know, debugging sessions are debugging sessions. The important thing is the techniques and the tools that I show here. So now I'm in protected mode, and it would always be better to disassemble things. But if we're in C code, it's even better to look at the code, right? So here, I even have the source code, okay? So it's pretty nice because it had the line information over here, okay? So for some of this, we have like the symbol information and so on, okay? And maybe I even have a backtrace, but no, I do not have this yet. All right? So for protected mode, the file is going to be pm.c. And you need to know that sometimes some functions, especially in the extraction of the kernel, are going to be compressed, are going to be inlined. So you don't always get everything that you want. But what we have here is like a well-known old workaround for enabled A20 gate. We have interrupt masking, setting up of description that needs to happen, and then the function protected mode jump that gets a parameter. Remember that I told you that under the header .s, we fill some code places. So there is a way to actually refer to it. And this code 32 start is going to be a word that is going to be filled in this header. So the data was not reserved, the space was not reserved in vain. Okay? So this is the protected mode jump. And we're still not there. Protected mode jump is going to be in assembly. And let's go ahead and do some single steps here. So now we need to get rid of the breakpoint because GTP likes doing problem. We'll delete them. I'll do ta-ta-ta-ta-ta. And this is enabling of A20, okay? So I'm going and do whatever I do. There's the A20 test. And I don't really need to do that. What I want to go is we write to some ports. I want to just go to this protected mode jump, okay? That's what I want to do. But now I'm past these things. And what we have here is like the last call before the protected mode jump was this call W to 0128F, which if I disassemble in object dump, I will see that this is what it is. Okay. Now, so this I did not build like the tags for the output here. So this is going to be this file, pmjump.s, and it has two interesting things. Okay, it's an assembly file that does this. The function is this one. It ends here, very short. Here we have at the end of it a jump instruction. This is long jump, okay, to a label that is under the .text32 segment that does these things and then jumps somewhere, the 32-bit entry point. Now, I will leave you as an exercise to explore this, like on the longer course I would do like everything, but we don't have the luxury to do it right now. But there are very important things here. First of all, those of you who understand x86 architecture and those of you who understand ARM, they are the exact same thing here, okay? Like with CR15. Sorry. So basically, it's not CR15. It's a register 15 of role register. I don't remember what at the moment. So what we have here is this. We do all kind of initialization, which is good, which is great. And look what's happening. We are going to see what is the status of the control register 0. And there is a particular bit that we OR in it. And then we're going to set this bit in CR0. But we will not be in protected mode until we actually go and enable this jump. Okay, so we need to jump, to do a long jump. And when we do this long jump, we do this long jump to a function that looks like this. So let's single step these things, okay? So now I'm going to single step, single step, single step, single step. Now I'm going to set up the CR0. I will not see it in the register map, okay? So I'm single stepping, single stepping, single stepping, and look at the address that I want to jump to. I want to jump essentially to 10,000 plus this. Sorry, to this plus 100 plus 10. Okay, I need to multiply by 16. However, do I really do it? What does this jump do? What is the meaning of like a jump when I change mode? So these are like the thing that on x86 can be a little bit confusing. Okay. So I'm now on the jump. My current segments are CS is 1000. Okay. And I'm going to do the next instruction, and I see that CS becomes 10. Okay. However, the jump that I have here is still on the same segment. So I didn't even look at the code segment, which is what's happening in protected mode. Okay. When I'm in protected mode, I do not longer use the segment for addressing. So this is what's happening now. Okay. And this is what I'm running. Sounds fair? So what I disassemble now, this address that actually takes into consideration the code segment, is misleading. So I need to get rid of it. What I need to do instead, undisplay one. What I need to do instead is to display the program counter. And look, surprise, surprise, the program counter is the same. Like I'm looking at 13181, okay? Sorry, 13081. So the 3081 from like the jump, I actually see it, okay? But now, this long jump, I transfer the segment, but nobody cares about the segment. I'm still in the same segment that I was before. Speaking of what I execute, even though the code segment changed, the register itself changed. So I'm now in the same address space, okay? And now you can see that I see the addresses, the instructions that are exactly like this. Fair enough? So the last thing that will be here is EAX. And what is EAX? If we looked at the code, we see that there was an argument to protected mode jump. And the argument to protected mode jump was EAX according to the calling convention. You can see that nobody touches EAX here. Nobody touches in the code. I did search, nobody touches. What was the parameter? The parameter was this friend, that you can actually find the address of it like very, very easily. But I'll just say, okay, so what is EAX? EAX is 100,000. So when I do this, look what will happen now. Boom, I moved to 100,000. Great. This is really great. But what is the problem now? There is no problem really. But there is a challenge because all the addresses that I had when I put the symbol file were expecting to have the memory starting execution from 10,000. And I can guarantee you that everything that we had in setup.elf, let's do like this disassembly. This is the start, okay? 0. And this is the end. That is, okay, debug ranges, never mind. That is a couple of thousands, okay? Now, there is a huge difference between a couple of thousand and 90,000 in the best case, which is like the difference between 10,000 where we started and 100,000 where we start now. So we have a problem. So we need to realign our symbol files, okay? Otherwise, if we want to debug, we will not feel comfortable. We'll not know what's going on. Fair enough? Okay, so I will now go ahead.
I missed the last sentence. Can you repeat that?
Excuse me? Yeah, what I said is that before we did this jump, before we enabled protected mode, we were in addresses that were like in the range of 10,000, okay? And we do a jump to a place in code that has the address of 100,000. This was the jump EAX. This was the address, okay? Like I saw what was the address, and it was 100,000.
Mm-hmm.
Is it clear now?
But how can you jump outside the range of the code register?
It's not. It's not. This is the change to protected mode. So
okay.
Things look different now. Okay.
Okay, I missed that. Okay.
So there is something in this address. Okay. It's not that there is nothing in this address. You bet there is something in this address. Question is, what is in this address and why, and what is going on? Okay. So the symbols that we have, they will not represent the reality. So there are several techniques. One of them is to go like over the. One of them is understanding what's going on, having the experience. I can do it. Okay, I know what's going on. Another technique is to go and disassemble everything and find code that looks more or less the same and hope that GDP is not wrong. Okay. And what I'm going to do now is do a combination like of my knowledge. I'm getting rid of the symbol files. One of the annoying things about it, when you discard it, you need to discard it because otherwise if you add symbol files, that it doesn't always work if there were symbol files before that or if the addresses are different. One of the problems is that it resets also the display. Yeah, but it's not a huge deal. There are ways to take care of it like with GDB anyway, okay? So what we're going to do now is what I call like the second phase. We have like the jumping, okay? This is where we finished. Now, I can actually detach and load another debugging file, but you know what? I'll do it manually anyway. it wouldn't hurt. So it's going to be protected mode something, compressed startup. And what we're going to do is the following things. We are now at this point, okay, where we were in 100,000. This is what we did. We see the following thing. We see that there is 100,000 and we have like a jump over here, okay? And if it's like not equals, and we have like the continuation of this. And we have a call to 125, which is the next line here. Call and we did. Okay, what happened if we see some more of these? Like what is even happening? What is this address point? What is this entry point? So here an experience is needed, okay? And the symbol file that we'll be looking at is something a little bit different, okay? We're going to go and look at things in the compressed directory, okay? Now, let's have a quick look at what's happening in the compressed directory. And for the sake of discussion, let's open another one. So under compressed, we have a file called head32. Okay, and we have this file VM Linux, which was linked, as I mentioned before. I'm not going to do it again. And if I do optimp -d to head32, I will see that it has a text section. And it has a head.txt section. Look at the numbers, there are 0. This is the object file. And we see things that look pretty much similar in this startup 32. I mean, okay, I see the number 25, and I see the moving of registers, and I see the clear direction flag. Let's see what's happening in VM Linux, okay? So I'm going to go and load it. And I see that in startup 32, voila, I see the exact same thing. Okay, this looks nice. This looks promising. What happens if I go ahead and try and load this one with the section net.txt in the offset of 100,000? Maybe things will look clearer to me, maybe they will not, but let's give it a shot. I mean, why not? So look at this. We have here several things. So ignore the comments that I have here, okay? The comments like for full demonstration. We can go and add the symbol file. But here we have an address. 147 DEA0. What is this address? What is going on here? So this also looks like very, 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 very high, speaking of like the numbers, okay? So the idea is like this. We need to be a little bit smarter about it. So being a little bit smarter about it is going to go and load the symbol file. Now, let me remind you again, we cared about .head.txt. So this one is going to go to our current address, to 100,000. And if we want text, if we care about it, we can give it as a parameter 11CEA0, which is where it's at, okay? So I'm going to do that, okay? And this is it. I'll put it in my debugger. I'll go to say yeah, and then I'm going to disassemble. So now in the disassembling, I still don't see what I expect, okay? It didn't catch .add.txt. It's not understanding it. It said, hey, I'm not playing nice with you. But you know what? It's okay. Let's go ahead and step. So we're going to step. We're going to clear. And we're going to call 100.025. 100.025 is just going to do a pop. And we're going to subtract and we're going to do things until something very important. Now pay attention to this line. Remember I told you that there is rep. Rep is going to run cx times. So if I look at cx, I see that it is 296,736. Now what is happening here? So I know that the file for this is head.s under kernel. And add32.s. And I'm looking for the rep. Okay? Which will be somewhere. I'm looking for startup 32. This will be easier for me. Okay. So this is startup 32, okay? It started and it had some jumps. So we have this guy, and we have clearing of the BSS. And look at this nice fellow here. We have all kind of like command line size that we don't care about too much. If there are configurations that are enabled, then we do some things, otherwise we don't really. But did I really pass 5C lines? What do you say? Do you think? Now back to what we had before. This is how GDB interprets it. It doesn't necessarily mean that this is how it is, okay? This command. So I'm just going to search for rep, assuming that I don't know, and I see that we have like, okay, repeats STOSL, okay? But we have this rep several times. The idea here is very, very important and very, very simple. What we're going to do in these lines is essentially copy the kernel to another place. Now, if we look here, this is still the output of the previous phase. What we're going to do is, after enabling the protected mode, this is where we were. We had a jump to 100,000. I proved to you that we're in boot head.s. Okay? We're now in this line. We're going to copy a huge amount from one place to another place. And then after that, we're going to jump to it. So let's see what are these places. Okay? So every time you have like a rep and something with move string or something like that, then the idea is that we're going to copy from DS, unless specified another segment explicitly, in the place of ESI, into the place of EDI. So in one command, we're going to copy all of these bytes and either increment or decrement. We decrement here because the direction flag is set, which means it goes backward in the copy. And this is going to happen CX times. So let's see what are the ESI registers and EDI. So we can see that ESI is this fellow here, and EDI is this fellow here. These do not exactly match what we were currently running, like we wanted 100,000, but it makes sense. You know why? Because look at the difference. We start from the end, and we finish one long before the beginning. Now, I'm not going to talk to you exactly how about it. Like, there are all kinds of optimizations that are done usually. Like, we divide by 4, and if it's like a multiple of 4, then this loop copies everything, and it's like faster. In ARM, we're going to do something pretty similar with store multiple data bytes and several registers. It's tricks to make copying more effective, okay? But the essence is that we're going to copy, and we're going to finish we're going to finish before the start address that we had, and we're going to copy it to another target that is much, much, much higher. Okay, it's going to be pretty much 1 million. If we looked over the code, we would see it with our own eyes, like how this is being done. So if I try to skip this breakpoint so many times, it will not work so nice. So I'm just going to do something else. I'm going to break at the next line. It's much, much slower to repeat a step instruction. And I'm going to continue. So I did not delete this breakpoint, I believe. I did. Okay, everything is okay. So what I have now is this. ESI, first of all, ES6 is going to be 0. Because I finished. ESI is going to be 1 byte, sorry, 4 bytes before where I started. That is 100,000. So pay attention. If I add to this, so that is 10,000. I'm sorry. This is where I started my code. And EDI is going to be this address. Okay. So what I essentially did here, what I had like in this address and what I'm doing is copying from this place in memory to the other place in memory. So if you add to this, you get 100,000. Okay. We have here 4F and 1C. Let's see if we have the right bytes indeed. So let's look just for fun. 40x on 0x 100,000, and let's do the same on million, and it's not the same. Why? Because million is not the address. Okay, it's an offset from there more or less. So if we go ahead and do the same thing on what EDI is after the loop, which is this guy, plus 4, okay? Then we will see the exact same data. Okay? So that's what we have. Then we clear direction, we save ESI. There are reasons for that, but never mind what they are now. And then look at this. What's happening next is that we're going to load. You see this nice fellow here? It's an offset. It's an offset that we saw before also, when you look at the text. So let's look at this offset. It's this one, okay? 11CEA0. So we're going to take this friend, and we're going to add it. And where were I? We're going to add it to EBX, okay? And then we're going to jump. So let's see where it is. This is the jumping. Wait, I'm not sure this is it. See, like, it's not so easy to do things necessarily, and it's definitely not it. I think I went too far. I think it's this one. I think it's startup 32. It looks like it. But where is EBX here? For the jump. No, it's not this one. This is the place where I need a break. And I just want to make sure I'm in the right file. I mean, the source code doesn't really matter. What matters is like what's actually happening here, okay? Because I'm not sure. I didn't look at the code at disassembling because I wanted like to explain like the features here. So just let's see what is EBX and see that like it's not bluffing. EBX is indeed 136,000, which is the offset that we have. If you build kernel with other kernel configuration, more symbols, less symbols, sizes can change sometimes, okay? And these are what the Z offset and V offset parameters are. So we're going to add this to this offset, okay? And we're going to jump to it. This is what we're going to do. So when I do this load effective address things, then the address of EAX is going to be 147 DEA0, okay? So I have the same code, but executing in somewhat different label. And by the way, this is what it is. I'm sorry, I'm so tired of looking so much at the screen this day that I just didn't even see it. So this is what we have, like the load effective address from L relocated is this function, okay, down here. That is a very important function that I will cover next. And what we have there is, so we're going to jump there, okay? So I'm jumping there. And there I am indeed. But again, the last time I adjusted like the symbols was on a different address space, and now I want to adjust it again. So since I've done that, I'm going to add a symbol file. And since I know that this address is actually in the text segment, whatever is going to be executed, then I can afford to actually go ahead and proceed with that. Okay, so let's go ahead and do that. All right. So I will get rid of the previous symbol file because otherwise there might be some problems. It's a stupid GDB bug. And now I will try to see where we are. I'll do this for the $PC. And look where we are. We are in the function underscore text. Okay. Now, why is this the name of the function? The reason for that is that this was like how it was defined like in the linker. And this label is not global, so the linker doesn't know it. I mean, it's just local, okay? But we see that this is like the text section and it starts here. So it gives it the following address, pairing symbol, okay? Now look what's happening here. Actually, a lot of things happen here. We have a call to something called extract kernel, okay? And here you see like the other code that we have is, for example, malloc. What is this malloc? It's not what we would expect. So let's go back to see some more white view, okay? And let me get a sip of the drink. Okay. So what we did, we copied the line. This I proved. And this will leave it. We did a relocation, and after copying, we actually went and jumped. So here I gave like also like an example of how like the memory looks, that it's identical between the 100,000 and like wherever I got in, and we jumped to the relocated address. Okay. So this I already did like the symbol matching, and this is the phases that we actually did. Okay. So what's happening here? What is dot relocated? What is the function that we're currently at? So it does several things. It sets like the ESI mode for later, real mode if we need to jump back. It makes room for something that looks like execution environment, like makes like its own heap. It's not what you know for if you use KMalloc. Like you're not going to have slab, you're not going to have anything there. You don't even have pages there now. Like you don't have anything, right? It makes some place in order to prepare things. And it extracts the kernel. What does it mean, extract the kernel? Remember that before I told you that we have a kernel that was compressed, and we had this piggy guy that takes care of like having compressed kernel in an object place. So extract kernel takes this, and according to the algorithm that is defined in the kernel config, for example, in my case, it's XZ, it inflates the kernel. Now, one of the reasons that we inflate the kernel to an address that is much, much, much higher, like 100,000, like we did now, like 1 million that we did now, is so that it will be far away enough from whatever we had before, and that will have enough place to extract in place. That is to not do another relocation after that. Okay? So what we have now is this extraction. And to make a long story short, the extract kernel that is under misc.c, it is going to print all kinds of things to string that I told you that are printed. You already saw it yourself when I made the example without the debugging. And it's going to make sure that the file itself is one of the things that we're going to do is like call the compressed, that sort of object oriented is going to call the exact algorithms and wrapper to take care of XZ in my case. And then it's going to call parse elf that will actually look at the section, at the program headers and move them to the right places, okay? And perhaps we'll do additional relocations, okay? So let's have a look at what's going on in some of these things. Fair enough? So I'm going to, now I'm in label relocated. And here, once again, we have like a long copying, okay? But so I'm going to skip that, and I'm going to go to extract kernel. So I'm going to put a breakpoint in extract kernel. And because I already added hardware breakpoint, I can use regular breakpoint. And here I can see that I have all kind of copying and jumps and stuff like that. But I want you to see that I initialized the console. I want you to see that I wasn't bluffing before we proceed. I don't bluff, okay? And I'm going to do like this breakpoint after put str, so that you'll see that there is another print over here. Early console in extract kernel, okay? And here we have several prints that I'm going to pretty much skip, at least some of them. And what I'm going to do, let's do a temporary breakpoint in wherever is highlighted to see what was done here. And we see here, input data len, you see this guy's output, that is where, oh, this is the value of a parameter called output, where I will jump after I extract the kernel. So this is what I have. So now I'll go and be a little bit, I'll go a little bit faster. And we already understand that this is like what's going on. This is the kernel that we have. So I will break after this point, okay? After we already extract the kernel. What I can also do is maybe put a breakpoint at parse elf. I think there is such a file. Info address parse. No, it doesn't recognize it. So it means it was inlined. Okay, now I accidentally did continued. So I will do the process again, but this time a little bit faster. I do want to show you one thing though. What is extract kernel? So under misc.c, we have this extract kernel. It's source file. It's a little bit easier to see. And we see like the prints that I put here. We see early console in extract kernel before we saw like the other prints. We'll have debug put str, which are only if we have a particular debug put address or put str, this thing, only if config verbose is enabled. And then we have these things. We have decompress, that is going to have a lot of online code, parse elf, and the relocation and debug put str. In this case, there are no really relocation. So the last thing that you see that like debug boot in the kernel is something that you're going to have. And we're going to return 1 million here, which is the output. So parself, what does it do? Look what it does. It is going to call, it's going to check that the header of the address that it receives were extracted is elf, 7f elf, that's what it is. And it's going to print like parsing elf. It's going to allocate program headers, remember them? And it's going to go over them and check for the ones that are marked with the type ptload. And it's going to just go ahead and move the memory according to the offset that the elf header has here. Okay? This means, in other simple words, and like if we have more time, or if I didn't show code, I would actually show how I break and how I show it line by line. I really like showing it, but now I will not do it because we're recorded, and the entire session is pretty long. It's almost 3 hours already, right? So the important thing is this. Pay attention like to the left-hand side, okay? So we have this VM Linux guy. It is an elf. And I'm going to do read elf dash L, I think. L section or H. Which one do I need? To VM Linux. Yeah. So it's going over everybody who has load, which is this guy only in this particular case. And it's going to look at the address. And if the address here was different, then it would add the offset. Where would it add the offset? To the output address that was given here plus the offset. So I just move parts of memory, which is a very important thing in what your user space dynamic linker does when it says all kind of things like addresses to load like symbols that are not like in the same place, like addresses that are in shared libraries and the like. Okay, so this is what parself does. So after parself is done, then we return output and we see like okay, boot in the kernel and return output and so on. This is in the call to extract kernel. Okay, so back to the script I took like the information from. I'm going to now source it and run it, and I'm going to break in the address after the relocation. Okay, so these are the things that I'm going to do. I'm going to use now the file kernel head32 with head.txt at the new address. Okay, so let's do this. I'm going to comment out the 5th phase for now, and I'm going to comment out these guys, and I'm going to also get rid of this. We already saw it. We already saw the copying, so I'm going to get rid of this. And yeah, we already saw this, so I'll get rid of this also. I will break it, extract kernel. So what I'm going to do now is this. I will rerun. And I will use gdb-x, the file that I just edited. So debug. x86 protected mode. Okay, so it's going to be gdb-x on this one. Next time needs to be shorter. Been teaching for like 10 and like 12 hours today. If we call this meetup teaching. So I ran it, I loaded the symbol files, okay, and I'm going to continue. So I'm right in extract kernel, but look what I did. I did not adjust the symbol files to it. So I'm in extract kernel, and I put the breakpoint like after it. So I'm going to do your cont, and look where I am. See at the left-hand side, we have like the messages from extract kernel. We could, if there are requests, I will do whatever you want. I just need requests. I can do also like a small recording, like I did the addendum for the previous one. And then I show you how I walk through this phase and how the extract kernel looks, how like the zip looks, how parself looks. But the ways, as I said before, like when you go in jail, you look for a friend. You search like for a put str, you know what it's address, and you debug backwards, for example. That's like how stuff works. But here, we jump under this 1 million to the following code. And the following code is doing something that is interesting, okay? So relocate jumps here, okay, to the address million. That is exactly what we see here, but now I added debug information. And this is going to be not only in protected mode, but also move to page mode. So some of the things that you'd want for debugging, because we'll finish soon, is that this is the source file you care about, kernel head32.s. The object file is add32. The section where we start is .add.text. This is why I put it in a debugging script. And you can actually use the VM Linux file. And let me explain. The VM Linux file from the top directory, it will look as follows. If we do like opt-down on VM Linux -d VM Linux, we will see that this is the same function that is called startup32. However, it starts with C. Now, those of you who have experience with different paging modes, then it means that everything here is paged. And if you want to like get to the address, to the physical address, then you need to subtract this page offset, it's called, like C00000. Okay, same trick for every architecture. It's not necessarily going to be C, the address. And x86, 64 can be like much more and so on. Okay, same for ARM. So this is what we're going to do. We're going to look what this file does. And this file does some things that are very, very, very interesting. Okay, after we put this breakpoint, the function is going to check for processor features. For example, if it's like x86, then which special features it has, which version of x86 it is, and so forth. It's going to set up the page table, of course, assuming it supports paging. If it doesn't support paging, then there's no game. But in ARM, for example, there's also like no MMU configurations, and then it doesn't like do paging. It does other things, okay? So there is enable paging that sets the register in CR0 and points to the page table in CR3, control registers. And then there is a jump. Now, what will happen on the jump? Pay attention to what we have here. This is like the code. The code says, okay, move to CR3 and long jump to boot CS and 1F. And this is 1F, this is boot CS. Like it's the next line, okay? This is what it is. So this jumps here, but look at this. Before this switch, we have the prefix of 1. And after the switch, we have the exact same function, okay? The exact same code is happening next. But the prefix is C. And then you can use VM Linux for the debugger if you want, okay? Now, after this, just so you have context, we're continuing executing. And in the execution, okay, we will later have a function that calls this address. It can be different addresses, of course, depending on the kernel. And it calls what is inside this address, which is a symbol called initial code. So initial code points to this address, to C12B680C. And inside of it, there is an address that we jump to, that is this guy, C12BF1B5, okay? And this address will call start kernel. That this start kernel will be in a head32.c, and we'll call start kernel that we know from Linux, okay? Which will look like this. So I'm going to show this, and after that, our mission would be successfully declared as very successful, okay? And I gave you like enough attention and enough time to do and reproduce the things that I do, and not just said, okay, like this is the slides, or these are like the phases. So even if you didn't understand 95% of what I said, but you're motivated, you can go and teach yourself, not only on this particular architecture, on every architecture. On 64 mode, by the way, it is the same. So let's just go and do like the last phases, okay? I wanted to see with your eyes what happens when you do paging. And this is also very relevant for ARM because it has like the same thing that I will show in this next video that will be shorter. So this is startup that comes from somewhere. We already know from where, okay? And we can go and we can jump and we can see. Now, back to some, I can go and show it like in object dump, but I believe that I already have like the addresses here. So what I'm going to do now is break in 100.118. So let's see what is this address. Maybe we're close enough. 118. So we see that from here we will call a startup SMP. So let's see what is the value of CX here. It's pretty intense. So I'm going to go and do a break, let's say in startup SMP. Let's disassemble. '60i on startup 32 SMP. And we have verify CPU and all kind of things, so we don't set like pages yet. So I'll just go ahead and put like show you like the breakpoint, okay? Show you where start 32 SMP is, and I will put the breakpoint like directly. So we'll do two things. We'll see in the source, and this is not it. We already are in kernel, okay? And so startup head 32, sorry. Startup 32. So there is startup 32 SMP, okay? That is going to be called, like here at the end. So sorry. It's going to be called, all right? There are several indirections here. I'm not going to go into them like now. But startup SMP is going to do the following thing. It's going to set registers, and it's going to go and check like what is like the value of this page table. It's going to set all kind of flags. It's going to check before we check like processor ID. You'll see the word CPU ID several times, like to check for features, okay? So what we're going to have now is jump into enable paging, which is where I'm going to put like the breakpoint, okay? And enable paging, look what it does. It's going to set the page table pointer into CR3 register. It's going to set the corresponding state to CR0, and then it will jump. And upon this jump, the addresses that I see, they're going to change. So I'm going to go and actually jump directly to there, okay? So let's continue. And these are the addresses that I see now. And then I have a jump. Pay attention to what's happening, like to 10. And with C111F, which is this address, only C to the left of it. So when I do NI, Pay attention. This is the next address, and I lose again debugging information. But it's not a big deal, because now what I can do is use the information from VM Linux. So I can, because I already care about this, the text segment now, I can just go ahead and say that it's file. VM Linux, I can go ahead and do disp to $PC, and then we see the exact same code, okay, as before, just one line after. This was before. This was the jump, and now we start here. Okay. And now we can start. We can navigate. Setup once is a function that is called only one time for the CPU. There's a nice trick there that also uses like the header. And we can move here, move, 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 and then we go to i386 start kernel. And this nice function here is in head 32 without underscore. And it's exactly this particular function. Okay. And this nice particular function, pay attention to this and pay attention to what we ran here. Still no output to the terminal. This particular function is calling ftrace. I can do it later. It's just for tracing. I start kernel. It calls setup handlers, interrupt gates, x86 stuff. And at the end, what I want to do, what I really care about, is like the call to start kernels. But by this one, I have some frames information. However, I cannot really debug it like in a normal way, because finish will not really work here, because like the call here was like, I don't have the stack for the stack set up, like the stack frames are not set up properly, so GDB gets lost. But I can very, very, very easily see at this point that if I like put the same breakpoint here again and put a breakpoint like at this address or at start kernel itself, then I will jump there. So let's do this, and by this we will conclude this demonstration, okay? So I'm going to once again restart it. I'm going to now source the file because I don't want to break here anymore. So I leave this guy, okay? I leave pretty much all of them. I don't care about this one, and I don't care about the symbol files. I want to work with VM Linux because paging will be enabled. And I'm going to put a breakpoint right here, and also put a breakpoint at start kernel, okay?
You still have also a breakpoint a bit up.
It's
Go
okay.
back to the file? Ah,
thanks.
Okay.
So I indeed got to it. Let's delete it. And now in breakpoint 2, like I put everything in like the compressing kernels and the like. I also add the disassembly next line apparently, and not disp. Do I have display? No. So I'll do display. And now I'm in start kernel, and I will just put a breakpoint here. And it can be a regular breakpoint. And look what's happened. Like we have like the jump to start kernel, and this is start kernel, okay? Like I have here like the print K, that will be the print K for the banner. Let's go and set something over here. And we'll do cont. And okay, still didn't like, I did the print K, but the print K, like the buffer, print K is not like, it doesn't work immediately, okay? It prints to a log buffer. It prints to some place that is called the log buffer. So I'm not even sure what I printed there. So I will X. What is the problem with it? Ah, I need to look at the address, I think. So look, this is like this is what what it caused. Like I printed like to log buffer, and basically all the nice things that we know and love and care about are going to be like here, okay? So if I want to now go ahead and I already know where my file is, and this is something that we covered like from before also. And then I can go and see in init main.c. This is the code that we have. We're under start kernel, okay? And I can, if I want, put breakpoints in all kind of places. For example, if I want to go to rest init, where I'm going to start the first process, okay? So that's what I'm going to do. I'm going to break at rest init. Hopefully, I did not, like, it depends if I boot with KSLR or not, because I could actually fail over there. These things could happen, but let's, you know what, let's just give it a leap of faith. I'll break at rest init. If it doesn't work, it's because the address is incorrect, okay? So let's disassemble rest init and hope for the best. Yeah, it looks right. My kernel thread is like here. So what I'm going to do is continue. And indeed, I stopped at rest init. And the output, if there is output, will be here. Pay attention. And now I can go and continue my moves and so on. And I will continue here. I will delete all the breakpoints. And I will see init working. And this, my friends, have been the debugging session that shows like how to go from like very early boots into init. So the concepts are similar for x86 64, for ARM, for everything. And in the next video, that maybe will be shorter and maybe will be recorded, or maybe I'll do like another spontaneous meetup. I will actually go and show this process for ARM. So that's all for now. Are there any questions? Okay, so that's all for now. If anybody is interested then to speak in our next meetups, then please let me know. Already gave the details. The name is currently embedded Israel on meetup.com. And if anybody wants to attend, so this week I am teaching the Linux kernel course, but if anybody wants to attend an Android internal course next week, then it is still available. And there are still a couple of slots to register in. It will be in US time zone, actually. So let me just go and see, like, I posted like on Twitter what would be like the link for that. Pretty sure I posted LinkedIn also. Let me quickly just show you the link if anybody's interested.
I do. If you can send the link, it would be great.
I'm not sure if you can afford it with what you get from the army. If you register to it independently, then it's okay.
Okay.
And so I did not massively. First of all, it's better like if you want, like you can contact me directly, and I'll like also make a discount for you. You don't need like to go to Eventbrite. But basically, the Eventbrite is going to be this one. So it's going to be this. So that's going to be the link for now. And yeah, so if there are any questions about what we talked now or any requests for like next sessions, I'll be very happy like to help you out, okay? And if you want to talk or ask questions or anything, these are my details. And the next talk will be about the initialization process of ARM. Okay, it will be, if it will be recorded, it will be shorter, because we covered all the ways to debug and like to teach yourself how to do this. We covered it completely. And if not, then no. Okay, so this will be uploaded to the YouTube channel. If you know people who wanted to attend but couldn't do it, just let them check that. Okay. So, yeah, question?
No, I just wanted to say thank you. And I wanted to ask if you received my call for papers.
Yeah, I did. I'll talk about I'll talk about it with you offline. Okay.
Okay.
So this is the link, like for the Android internal course, and I usually do courses with people that I like know, or I do these things, like I don't really publish too much, like. So we're going to go and dissect some of these things, and maybe next time I will better announce it, and that's it. Okay. So this has been our session, and I'm looking forward to the next one, and looking forward to hear great talks at Embedded Israel meetups. So thank you for taking the time to attend and learn, and have a good one.
Thank you.
Thanks a lot.